I think this is probably the time that we should get back to the class. Okay, so is there any question about the center selection problem? I think we are a little bit hurry in time to finish the proof that this greedy algorithm, that our strategy here using the observation that maybe a good strategy is to repeatedly choose the next center to be the set farthest from any existing center. And actually using this kind of strategy, we gave a two approximation algorithm. And basically finishes the proof here. So is there any specific question about the proof here? I think at last I mentioned this theorem, unless P equals to NP, there is no real approximation algorithm for the center section problem. For any constant whose rho is smaller than 2, this is not required, in this class. This proof is going to be using more advanced results, but this is just to showing that this greedy algorithm actually for this is already like the best algorithm that we can hope for, although it's actually quite simple. Okay, so is there any question for the center selection problem? Okay, so if there's no question, let's talk about the last part of today's lecture. I think basically the last part of the whole class, which is knapsack problem again. Okay, so I guess we have been probably familiar with the knapsack problem. So in particular, the knapsack problem having the following things. So in particular, given n objects and a knapsack. And also, actually, we know that assume atom I weighs the Wi, which is larger than 0 kilograms. And this value of Vi larger than 0. And the knapsack has a capacity of W kilograms. Okay. So the goal here, is that we want to have like a full knapsack. Right. We say field knapsack was a typo here, so as to maximize the total value. Okay, so this is some problem that we are actually quite familiar with. We know that actually when we talk about dynamic programming, we actually know that the knapsack problem can be solved by dynamic programming. So in particular, how do we achieve that? So we have this definition of like a two input function. So we have this function OPT I W to be the max profit subset of item from 1, 2 until I with weight limit. So the first case that we know is that we consider the case where the OPT does not select. Well, for the case where the OPT does not select item I here, we know that actually the OPT is actually going to select the best of 1, 2 until I minus 1 using weight limit. But for the second case where the OPT is going to select going to select the ith item here. So in this case, we are going to have a new weight limit, which is going to be a w minus wi. And then we know actually the OPT is going to select best of 1, 2, until I minus 1 using the new weight limit. Okay, so as a summary, we can actually have this kind of relationship. So in particular, OPT of I W, actually it equals to 0. I mean, if I equals to 0, of course, if you don't have any item, the OPT value is just going to be 0. And the OPT I minus 1 equals to OPT I minus 1 W. So if actually, I mean, Wi is actually larger than W. So if the ith item is just so heavy, I mean, larger than your current W, you just cannot choose that. So you know that OPT is actually, OPT IW is going to be OPT I minus 1 W. And otherwise, I mean, if we have some item and actually Wi is smaller than or equal to W here, this is going to be the max of OPT I minus 1 W. And if we choose the item I here, it is going to give us a value of VI plus an OPT I minus 1 W minus W. Okay, so this is just a very quick recap about the dynamic programming algorithm for the knapsack problem. I guess you're probably familiar with that. So I'm just writing all the things down here without further explanation here. And I guess you can probably recall that the running time of this algorithm is O of N W. And one thing that we mentioned, I mean, in terms of the knapsack problem, is that actually this is not polynomial in terms of input size. And in particular, we have this W here. I mean, just imagine a case where for instance, maybe the value and the weight, they are just huge. So in particular, I mean, let's just for our convenience, let's talk about a case where the item maybe there, for instance, have very large values. So maybe let's say that, and I think let me just draw a table like this. So assume that maybe we have a few items. So let's say we have item 1, 2, 3, 4, 5. But actually, if the value is something huge, if it is something something like this, maybe something like this, or maybe something like this. I'm just writing something random here, but just some huge numbers. And the weight here. I mean, assume that for this case, the weight is small. So I'm actually going to introduce another algorithm here using dynamic programming, but actually it is focusing not on the weight here. It's actually not focusing on the weight like this, but focusing on actually, excuse me, but actually focusing on the values. I'm actually going to introduce an algorithm like that. But nevertheless, I mean, you can see the intuition is that in general for a problem like a knapsack problem, if you have an algorithm which is not polynomial in terms of input size, I mean, if your value is just huge like this is probably really bothering, and maybe for some boundary case, this is really difficult to judge that actually which case is better than which. So this is actually going to be a little bit annoying. I mean, in general, for the knapsack problem, if you really want to find the optimal solution, this is in general, actually the knapsack problem is also an NP complete problem, but we won't have time to cover the proof here. So actually, we can prove that the knapsack problem is an NP complete problem. It's just like the case where, for instance, if the width is really huge or the value is really huge, at some boundary cases, it's really difficult to make some judgment. But on the other hand, nevertheless, and actually for a problem like the knapsack problem, I mean, if you're okay with the approximation algorithm, I mean, if you're okay with, for instance, your value is a little bit off from the optimal, but very close to that. Maybe, for instance, in this case, I mean, if all these numbers, I mean, if all these numbers are really huge, I mean, It's probably a little bit annoying, but maybe instead we can consider something like this. So assume we have the item value. Wait. So maybe instead we can consider something like this. Okay, so the item index is still going to 1, 2, 3, 4, 5. So here the weight is actually quite simple. So what if, I mean, we significantly shrink the size of the value here? So maybe, for instance, let's just look at the beginning part of the number here, or maybe make this even smaller. So let's divide all the numbers by approximately 1,000. So for instance, I mean, assume that this is 2, and this is maybe 7, and this is maybe 19, 23, 29. So this is probably much more reasonable. I mean, this is like a much more reasonable case. I mean, as long as you don't want to find the exact solution of the knapsack problem, you're okay with a little bit of approximation algorithm here. You can significantly shrink the size of the value here. And that is actually a very important observation here in terms of that basically for a problem like the knapsack problem, I mean, the precise problem is actually very difficult. It's actually an NP-complete problem. But for such kind of problem, knapsack problem, actually exists very good approximation algorithm following that. And in particular, I mean, the idea that we can actually talk about here in terms of the approximation algorithm. Is that basically we can just round up all the values. Okay, so why is this helpful? So as I just described, so here I think for the original dynamic program algorithm, we have been really focusing on like the weights here. But actually there is a second dynamic programming algorithm that actually can focus on the values. And this is basically going to be the place where we plug into our observation based on approximation algorithms. Okay, so how am I going to do this? So the most important thing for a dynamic program is that basically you need to have some sort of function, and basically you need to represent this corresponding function in terms of a recursive formula. So here, as I was saying that maybe we want to focus on the values, and hopefully we are making a rounding up for the values here. So here we are going to, we are going to follow a similar pattern here. Because here, I mean, for instance, in the dynamic program for the knapsack problem, we are talking about, I mean, the first parameter is an I, which represents like the first I items. And the V here is actually, sorry, a W here is actually represents like the value here. So here we are going to use another parameter here. I guess we are probably going to keep the I here representing the dynamic program has actually a process until the item I here. But actually the other parameter that we are going to use this time is going to be a V here. I mean, because we are using a V here, instead talking about like what is the optimal value that we achieve here. Here we the definition of the OPT IV here is that we are going to talk about the mean weight subset of items 1, 2, until I that actually use value exactly V. But here, for our convenience, we consider, I mean, the OPT or IV here to consider the weight subset of items that use value exactly V here. So this is a slightly different compared to the original dynamic program. It's not only about like a difference between W and V here, but actually we say that we hopefully use the value exactly V here and see what is the cause of this algorithm. Let me say what is like the relationship that we are going to deduce for the for this OPT IV function here. Okay, so the first case that we are going to have, is that actually the OPT does not select item I. So what is going to happen in this case? In this case, we are just going to encounter that the OPT is actually going to select the best of 1, 2 until I minus 1 that achieves exactly value v here. So this is the first case. For the second case, is of course going to be the case where actually the OPT selects item I. Okay, so in this case, I mean, after we select item I here, this is actually going to consume weight WI here, and actually the new value needed is exactly V minus VI. And then we know that the OPT is actually going to select the best of 1, 2 until I minus 1 that actually achieves exactly the value V minus V. Or formally speaking, we can actually write down the following dynamic program, the OPT of IV equals to the following. So it is going to equals to 0 if the V is 0. Exactly, I mean, the choice is that going to give you exactly value of 0 here. I mean, this is just going to be 0 here. Or if I is larger than 0, V is larger than, sorry, I equals to 0, but V is larger than 0. So in this case, I mean, we don't have any choice. I mean, basically we are talking about, because here we are talking about the OPT here to be the mean weight subset of items. I mean, in this case, we also don't have any. We also don't have any choice here. So in this case, we are also going to have a 0 here. But otherwise, we can also give a very straightforward formula here. So basically, this is going to be the OPT of I minus 1 on V. If actually, I mean, if the value, I mean, the value of VI is actually exist V here. So this is just going to be so expensive, and this is not going to be helpful for us. And or otherwise, maybe this is going to be the mean of OPT of I minus 1 V and WI plus OPT minus 1 otherwise. Okay, so is there any question about this dynamic programming now? Okay, so in terms of this algorithm, I mean, we slightly changed the dynamic programming algorithm in terms of basically as a function of the weight here. We make it here to be a function of the value. And basically for this problem, we know that actually the running time, is actually going to be the O of n V star. We are actually the V star here. The V star here is actually the optimal value. Or we can say that which is the maximum V such that OPT and V is smaller than or equal to W. So we know that actually the running time of this algorithm is going to be O of n V star, because this V star is the best possible value that you can reach to make the problem, actually the output makes sense. But actually we don't know what is the value of the V star here, but we know the value of the V max. The V max is actually the largest value in the original instance. So in any case, we know that actually V star is actually smaller than n times V max. Because in the most extreme case, I mean, even if we just pick all of the items, I mean, the V star here should just be at most n times V max here. So this is just due to the definition here. So The good thing for the Vmax, I mean, compared to V star, is that the Vmax is something just apparent. So for instance, here the Vmax is just this value. So this is just something quite apparent, and basically you know what this V star is. So basically, if you know the running time is O of n times V star, then basically, since the fact that based on the fact that V star is at most n times of Vmax, we know that this is actually O of n squared Vmax. Like this. Okay, so another thing that we can make observation here is that in terms of the Vmax, I mean basically the item with the largest value in original instance. So without loss of generality, we can assume the weight Wmax corresponds to this value of Vmax, actually satisfies, let's say Wmax smaller than equal to W. I mean, otherwise, even if you know that actually the Vmax here is really good, but actually its corresponding weight is already larger than your limit W here, you can never be able to choose that. In this case, it's probably, you just don't need to worry about that. We can just, we never select this item, and can simply delete it. But here, as long as we are talking about the Vmax, basically here we just assume that this at least it is selectable, and in terms of selectable, it is just the Wmax, the weight corresponds to the item which achieves this Vmax is at most W. Otherwise, we just do. Okay, so is there any question up to here? Okay, so the remaining thing that we are going to do here is that basically we are going to use the observation here, basically the observation here. I guess in general, for a lot of practical knapsack problem, it is typically the value is quite expensive and a little bit hard to, for instance, you have a little bit value, all the values like this. For the extreme case, this is extremely difficult. But basically, we want to round the values. Basically round the value to all this that is much smaller. And this is actually the place that we are going to attack the problem. And in particular, we are probably going to formulate this clearly that how we are going to make the rounding here. So we are actually going to do something like this. We say that actually to make this polynomial in input size. So basically, we are going to do things like this. So we are going to round all values. So we say that we are going to round all values up. So this is a little bit important because if you round it to be, for instance, like the closest integer, or this is going to be like larger than that or slower than that, this is going to be a little bit confusing. So we point out that we are going to round the values up to lie in a smaller range. So this is the first point. And the second point is, of course, that after you make the rounding, we just run dynamic programming. On the rounded instance. And after that, we just return on the optimal items in the rounded instance. And this is basically the strategy that we are going to use here. So I talked about the intuition that maybe we want to have like a specific rule about how we round the values. And here we say that we choose to round all values up to lie in a smaller range. So in particular, we are going to do something like this. In particular, we round up by consider something like this. So for each item, we consider this VI bar to be the new value that is assigned. This vi bar is actually going to equal to vi divided by theta with the scaling function times theta. And similarly, I mean, we have like another definition called the bi hat. Bi hat is just going to be this part of vi divided by theta. So the scaling function is something like 3.1 equals to 4, or 3.9 also equals to 4. It is going to be the closest integer that is actually above the value that we're talking about. Or if it is an integer, just return it. So here, I think there is a new parameter. The new parameter is the theta here. So here, we probably need to specify. I mean, also we were talking about the approximation algorithm. If you're rounding here, I mean, inevitably, you are going to have like a relationship in terms of some, I mean, for instance, you want to have like an epsilon approximation. I mean, sorry, 1 plus epsilon approximation, hopefully. I mean, this is definitely going to have like something to do with the approximation factor here. So here we say that epsilon is the precision parameter. And of course, we also need to specify what is the theta here. The theta here is called a scaling factor. And in our specific algorithm for the knapsack problem, we choose the scaling factor to be epsilon times V max over N. So this is our specific choice of the scaling factor here. So the epsilon is up to our choice. N is known as the input from the problem, and V max is also, I mean, you just like check what is the V max here. So this is, I mean, like calculating this scaling factor is quite straightforward. So we are later going to see why we want to choose this specific value of the scaling factor. But actually, a very important point, I mean, we're talking about, I mean, approximation algorithm about like rounding up all values. The most important observation here. The most important observation here is that actually the optimal solution. The optimal solution to problems with the problems. The problems with the bar width or the hat width, they are actually just equivalent. So I guess this is just straightforward because actually, I mean, they actually have just proportional to each other. I mean, if the two instances are strictly proportional to each other and for all the i's, the proportion is actually the same, then you can clearly see that the optimal solution to the problem with the bar width and hat width, they must be equivalent. And furthermore, the intuition, I mean, why that actually we can give a good algorithm for the knapsack problem. I guess this intuition is also not so hard to imagine. It's just that actually the bar V here is actually close to. It's actually close to V. I mean, basically, I mean, we are actually rounding here, but actually, I mean, using this rounding, this value should be not so far from the original value V here. So basically, the intuition is that the bar V here should be close to V, so optimal solution. So the optimal solution using V bar here should be nearly optimal. But also on the other hand, I mean, we know that actually the optimal solution to the bar V and the hat V, they should be equivalent. But also on the other hand, I mean, after we consider the problem of bar V instead of the original V here, we can just further reduce this to the problem hat V. And the problem hat V here is actually a small and also integral. I mean, because we are doing the rounding here, so this is still an integral problem. So we can still feel free to run our algorithm. And actually, the dynamic programming here is actually fast. Okay, so this is the intuition. And the final algorithm is actually a super simple. So the algorithm that we are going to use here is just that we run dynamic programming. we run dynamic programming. Actually the value version, which is basically this version. So we say this is the value version. Okay, this is the value. We just run the value version of dynamical programming algorithm here, but actually on the this is the ultimate algorithm that we actually use here. So in particular, the running time that we are going to pay here is that we know, basically based on the discussion here. Based on the discussion here, we know that the running time of this algorithm is going to be O n squared times Vmax. But here we are talking about a hat V here, so that is going to be hat Vmax. But actually here we know that hat Vmax, it is going to be equal to, based on our definition, based on this definition and the choice of the scaling factor here. So this is actually going to be Vmax, the scaling function of Vmax over theta. And we know that theta is actually epsilon times Vmax over n here. So this is actually going to be the scaling function of n over epsilon. And this is actually going to give us that the running time is actually going to be O of n cubed divided by epsilon. So this is actually, compared to the original algorithm, with this complexity. Or maybe with the knapsack, the dynamic program that we talked about at the previous class in dynamic programs. So basically this complexity. So this bound is only contained of n and epsilon, and it is independent of the input. Basically, we only have this kind of n and epsilon as the final running time, and this is actually does not have the specific like the Vmax, V star or Vmax dependence or the W dependence in terms of original dynamic programming algorithms. So this is like a clear bound. And I guess the only remaining thing that we need to prove, a theorem, is of course, after talking about all these kind of intuitions that basically, supposedly, this is going to give a near optimal solution for the knapsack problem. And I guess we definitely need to prove it. So this is going to be something like this. So if S is a solution by our algorithm, and let's say that S star is another feasible solution. So here the proof is actually a little bit, arbitrary. We not only prove that actually we are epsilon close to the optimal solution, but in general we can prove that actually 1 plus epsilon, sigma I from S on bi. This value should be just dominate all the other possible solutions, and for any other feasible solution as star. They're going to have this. Okay, so let's finally prove this theorem here. The proof is that we are going to have this kind of chain of inequalities. So we are basically going to have two relationships. So as basically discussed in this intuition here. So the intuition here is that we are going to have two relationships. We are going to first relate the problem of V to the problem of bar V here. And then we are going to relate the problem of bar V to the hat V problems here. So in particular, for the line of inequalities here, we are going to show is that actually the summation of I from I star of Vi is actually going to be smaller than the summation of I on I star Vi bar. So this is actually just due to the fact that we always round up. We always round up in this scaling function. So this is actually saying that this is always larger than. This is straightforward because x is always, the scaling function of x is always larger than x. So here, when we can consider this bar Vi function, this is always larger than Vi over theta times theta larger. So this is the point that we say that actually a good thing that we always round up, and this very easily give us like this kind of relationship. So after knowing this, we then know that actually this is actually going to be smaller than I from S of the bar VI, because actually we are talking about the optimal solution here. So actually we solve the rounded instance optimal. Okay, so this is the second inequality that we use here. And we need to further understand what is the next thing that we can talk about. I mean, basically, we have like reduced from VI to VS to bar of VI here. And basically, this is implicitly the place where we reduce we relate the problem of bar VI to the problem hat VI. Actually, we utilize the fact that the round instance, actually we can solve it optimally, and actually based on our observation here that the optimal solution to the problems with hat VI and bar VI, they're actually just equivalent. So this is something good, but furthermore, we still need to make this back to the original problem. And the way that we are going to make this back to the original problem is just that we notice that actually we are just rounding this. We're just not, we are not like just destroying the problem. The rounding of something makes a lot of sense, that actually this is going to be smaller than I of S VI plus theta. And this is due to the fact that actually we never round up by more than theta. So why is this the case? We can still look at the discussion here. So when we rounded an entry to the closest integer, there is actually an inequality like this. So actually x, the ceiling function of x is always larger than x and smaller than x plus 1. So in particular here, I mean, we are talking about the bar of VI here. We then know actually the bar of VI is actually smaller than VI over theta plus 1 times theta, which is actually just VI. And this is actually the place where we use this argument. And after that, taking a close look about like what this is, I mean, we are taking a summation of all the I from S, and there are just at most n items. And we know that this is going to be smaller than n theta, plus the summation of I from S of VI. And this is just due to the fact that actually the cardinality of S is at most n. And this is the place, and actually due to our choice of the theta. So basically, this is the specific place where if you look back, okay, I choose the theta to be epsilon times V max over n here. So this is actually a place we can see that actually this is going to be smaller than 1 plus epsilon times sigma I from S of I. So here, maybe we probably need a little bit more calculation here. So it's just because that due to the choice of the value theta here, so we choose theta to be actually epsilon times V max over n. Then we know that actually n theta goes to epsilon V max. And basically we know that the V max, I mean, just choosing this maximum value, and actually without loss of generality, as we just discussed here. So we assume that actually the W max is actually smaller than or equal to W. So I mean, for an input problem, so for instance here, assume that here, I mean, the weight here is like 100 and the input weight is only like 10. You can just feel free to just delete this one because this item is never going to be helpful for you. And this is actually a point where we have assumed that actually the maximum, I mean, the V max is corresponding weight, W max is actually at most W here. So in terms of that, I mean, based on this assumption, we can always, I mean, like one possibility is just that you just choose that item and you just choose the Vmax item. I mean, this is always a solution here, and we know that this is actually going to be bounded by summation of I from S. So this is just going to be the fact because we are talking about the algorithm here. So basically, we know that actually the S here, so it's actually the algorithm that we are going to have such kind of guarantee, and basically we just finishes the proof. Or I guess maybe let me make this way too. Okay, so any questions? So basically for this knapsack problem, actually you can see that actually our approximation algorithm, I mean, compared to the load balancing problem and also the center selection problem, where actually the approximation ratio is constant larger than 1. So here for the knapsack problem, actually our approximation ratio is actually arbitrarily close to 1. Actually, if our approximation ratio is epsilon, we can give an algorithm with complexity n cube over epsilon, and this is actually quite good. Okay, so any questions for the approximation algorithm for the knapsack problem? Okay, so I think we basically have 10 minutes, and I think I would like to thank you all for your attendance, and guess this is basically the end of my lectures. And as I mentioned, I think basically for the next lecture, the class in week 14, we are going to have course presentations, and for the very last class in this semester, we are going to have an in-class final exam. So basically, this is the end of the semester where I'm giving presentations and introduce you basically about algorithm analysis and complexity theory. And I think maybe we can take a brief summary of the semester. So for the summary of the semester, I think basically in this semester we have been talking about like a lot of different things. So basically for the first 2 lectures, so we talk about the basics of algorithm designs and also about like a graph. And basically we introduce a few different problems like stable meshes and topic notations, etc. And also for graphs, we introduce a lot of definition related to graphs. So next, and I think basically the most important part of the semester is that we introduce 4 very important kinds of ideas for designing algorithms. Basically, greedy algorithm, divide and conquer, dynamic programming, and network flow. So for all of them, basically we have mentioned quite a few different instances, and really ranges a lot of different like scenarios, like those graphs, like for instance Huffman codes on information theory, and basically for instance also some geometry problem like finding the closest pair of points using divide and conquer, like numerical algebra problems like integer matrix multiplication, like fast Fourier transform, and also for instance like dynamic programming that really covers a lot of real problem, for instance like knapsack problem, etc. And also the network flow problem can also reduce to a lot of practical problems to that, all using this kind of ideas. So basically the greedy, divide and conquer, dynamic program, and network flow, they are like the most common ideas in terms of algorithm designs. And I guess basically for such kind of like a graduate course, I guess we cannot probably cover all kinds of aspects in terms of algorithm designs. But I guess basically after taking this course, I think it would be great that you can remember all these kind of 4 algorithm design ideas. So basically towards the end of the semester, we also talked about complexity theory, and after that approximation algorithm. So in terms of complexity theory, we basically talk about NP and computation intractability. So that really talks about like the definition of complexity classes like N, P, NP, co-NP, and also subsequently the definition of NP completeness. So all these kind of definitions among those polynomial time reductions are extremely important. And after that, we talk about the Cook-Levin theorem, the NP completeness of the circuit set problem, the 3-set problem. And subsequently, we can make reductions to a lot of problems and basically show a lot of the problems are actually also NP complete problems. And after having that, we briefly talk about some more advanced complexity classes like PH, P-space, exponential time. But actually, this is a little bit more advanced, I guess. It's just like for your understanding about how complexity theory, beyond NP is actually going to look like. So for this lecture, which is the last lecture, we talk about approximation algorithm. As basically, this is a perspective to show that, even though some problem, they're NP-complete problem, but actually we can still give a relatively good algorithm that is actually quite good approximation ratio to this. Okay, so this is like a very brief summary for the semester, and I guess probably the most important thing that I'm going to introduce, I guess probably you're also very interested in, is about the form of the final exam. So as I just mentioned, the final exam is going to take place in class on week 15, which is the precise time is going to be December 13th from the 10 over 3 p.m. until the 6 p.m. the full grade of the final exam is going to be 80 points. So as I described at the beginning of the semester, so the final exam is going to take the 40% of the final grade. So I just make the full grade of the final exam to be 80 points. So that just like divide by 2 is directly going to give you the point. I mean, the part to the final grade, I guess, which is probably going to be convenient here. So in general, the problems we are going to have a similar style compared to assignment problems. So in particular, I guess the final exam is roughly speaking are going to have these kind of components. So at the beginning, we have roughly like 15 minutes to talk about basic mathematics. So like the assignment 1, we talk about like asymptotic growth. And I think in particular, I mean, like in divide and conquer in dynamic programs, we have a lot of recursive formulas. And I think there will probably be a problem to examine whether you can solve such kind of recursive formula. So those are like a basic problem for basic math. And for all the 4 main parts, and I think basically for algorithm parts, and also in the complexity theory parts, showing the some problem is NP complete. So these are like 5 main parts that introduced in this class. And for greedy, divide and conquer, dynamic programming, and network flow, AP completeness, for this 5 main parts, you are expected to have 1 main problem for each of them. And each of them is going to take 10 to 15 points each. And there will be no question for like more advanced complexity theory beyond the NP. So basically for the more advanced part that I introduced in the last lecture. So there will be no question for that. So for approximation algorithm, basically for the thing that I talked about this class, so there will be no separate main problem for that. Although for one of the problems, I mean, one of the problem along the way of talking about greedy, divide and conquer dynamic programming, network flow algorithms, along the way, one of the problem we can actually give a relatively good approximation algorithm, and there will be 5 points, like a side question to ask about like the approximation algorithm. And I believe that this side question for approximation algorithm should not be difficult. So it should be, I mean, for that problem, approximation algorithm should be relatively straightforward. But I think this is just to examine that actually have a good understanding about what approximation algorithm is. Okay, so this is basically the plan for the final exam, and basically for the, I guess, for the whole semester. So is there any question for the final exam and in general about our course? Okay, so if there is no question, just remember to attend the presentations next week. And if you have not like booked a slot for your final presentation next week, just do that. So the link is actually posted in the important announcement that actually I posted in the course website. In the course.pku.edu.cn in the by email to you, and also in the chat box here. So just remember to book a slot for the final presentation next week. And also don't forget to attend the final exam. This is very important. I mean, some students have asked to have like a pass-fail grade for the course. So this is definitely okay. And okay. So by the way, if you want to apply for taking the final grade as pass-fail or take the final exam online, just you must make the application before the final exam starts. And actually, just for the convenience, and I guess we just we require that all this kind of requirements, I mean, for taking the final exam online or the pass-fail grade must be applied like a day ahead. So basically by the end of the December 12th. So this is very important. So basically for this final exam, you must remember to come. And also, so I need to point out that if some student didn't attend the final exam, that is just a sign of fail, no matter if it's a lighter grade or pass-fail. I mean, all students must attend the final exam to at least get a pass, or at least get a I think at least D above. A D above means basically a pass sign for the final grade. So all students must attend the final exam. So this is very important. Okay, so if there is no question, I think I would like to thank you again. So this is actually the first time that I taught this algorithm analysis and complexity theory class, and also in full English. And I guess this is really a wonderful experience to work with all of you. And I look forward to your final presentation, final report. The deadline of the final report is going to be the end of week 14. I will send a reminder, and also I will also send a reminder for that. And actually, don't forget to attend the final exam, and I will see you then. Yeah, thank you for all of you. Thank you.